So what you can see on the right is an illustration of a SAR acquisition that was made in the last days for interesting wind condition, and I'm going to start presenting a bit what the SAR is and what it can do, since some of you in the audience may not be very familiar with this technology. So just to start introducing the technology before describing the issue. So I'm going to present the SAR-derived ocean sea surface wind. So what is SAR? SAR stands for synthetic aperture radar. It's an active instrument that can measure sea surface roughness at day and night, and also through clouds. And thanks to the use of empirical function, also known as GMF, we can relate the roughness that is measured by the instrument to the wind speed, the wind direction, and the incidence angle. And through this such empirical functions, we can derive from this sea surface roughness measurements that was acquired over Corsica and Sardinia an image of the wind map that is shown on the right side, where you can see some quite intense winds under some western wind conditions, and you can see very large acceleration and deceleration due to topography. Such maps can be derived at a unique resolution of 1 kilometer, and typical errors that we get thanks to comparison with NDBC buoys indicate the root mean square error of about 1 meter per second, for typical winds ranging between 3 and 20 meters per second. But as Jean-François also already said, we have abilities to estimate winds also on the very extreme winds, up to 80 meters per second, and then we have some very good correlation score of 0.9, thanks to some additional capabilities of the SAR. These acquisitions today are made systematically over the European waters, thanks to the two satellites, Sentinel-1A and B, which can provide images every 1 or 2 days since 2014 and 2016 for the two satellites. And this is showing a comparison between what the SAR can see and what typically some numerical weather prediction model can provide. And you can see it's provided with the same color scale, so you can have an idea of the underestimation or overestimation that we can have between the SAR measurements and the model outputs. So what is our issue? The issue is that we have numerical weather prediction model that can provide wind field forecasts and analysis every few hours, but with a limited effective resolution, spatially speaking, about 10 kilometers. On the other side, we have SAR-derived sea surface wind field that are spaceborne measurements and that are available at a high resolution of 1 kilometer, but with a low measurement frequency every few days due to the satellite revisit time. So the main issue that we are going to tackle here is to try to see whether it's possible to use the SAR-derived sea surface wind to improve the spatial resolution and the accuracy of the numerical weather forecast model estimates in order to get both the high spatial resolution and the temporal resolution. So to do this, we've been studying two sites of interest. One which is located around Fécamp. Here, I guess you can see my mouse. And another one which is located off Girona, which is located off the boundary between France and Spain. And we have several hundred collocated cases of wind situation between ECFW model and SAR-derived measurements. And for the Girona case, we also have access to WRF winds with some additional variables, which are the sea surface temperature, atmospheric temperature, heat flux, pressure, and humidity. You can see some few examples of what Fécamp and Girona wind situation. So typically we have some two cases of very different winds between ECMWF and SAR, and the wind distribution show you the very different wind measurements that we have in between the two, and the same for the case of Girona. So we can have very different, even though collocated within 30 minutes, we can have very different wind measurements and model outputs. So we are, let's say, three key questions that we are also opening with this issue is, let's say we have on the left ECMWF outputs, and on the right we have SAR measurements. One question is, how close are the ECMWF model from the collocated SAR measurements. So this question indicates us whether there is some additional information in the SAR. The second question is, how often do we meet similar wind situation in the dataset? Because in order to try to reproduce a situation, it's most useful to be able to image it many times. So for a given situation, how many similar situations we have, let's say, in the model dataset? And that gives us information on what are the chances to observe similar situation. Then another question is, how reproducible are the differences that we can see between the SAR and the model? So let's say we have some similar wind situation from the model. We have the collocated SAR, and the question is, how close from one another are the SAR situation? So this is answering to the question, is this additional information that the SAR is bringing systematic or not? So we have studied through different metrics that I will present later on the two slides. And the first conclusions that we have is that all sites do not present the same climatology and may not be therefore as well adapted to this technique. Typically, what we see for the FECAN situations is that the model data are closer to the SAR than on the Girona dataset, so which may mean that there is less useful information introduced by the measurements. Second conclusion of this investigation is we see that the Girona dataset shows slightly more reproducible ECMWF situation than FECAN, meaning that for a given situation, we're going to have more sample of it. Maybe because we have, let's say, less different wind regimes. Another case, the last conclusion is that for similar ECMWF situations, the SAR collocated winds are also showing closer wind fields, which is encouraging in the fact that this is going to be a very favorable site to apply this technology, this methodology. And therefore, the next results that I will show are applied to the Girona site. But before jumping to the results of the site, just to introduce a little bit different sources of issues that can, let's say, hinder the emulation capabilities, because I'm going to illustrate a few images of some atmospheric phenomena that can add some local wind variability for a given synoptic wind situation. So these illustrations are extracted from the OVL platform made available by Ocean Data Lab. And we are illustrating several kinds of phenomena, wind streaks, rain cells, convective cell, atmospheric gravity waves. Typically what you can see in this situation over the Brittany coast, it's a case of northeastern wind, where you can see some variability between the different wind alleys that are created transversally to this wind situation. And this is the sea surface roughness. And if I move to the wind field, you can see now that there are some alternates of yellow and orange, which are creating this wind variability. A second example in this case is a typical case of northwestern wind, where we can see this type of patterns that are characteristic of rain cells that are adding on top to the, let's say, synoptic wind, and which are creating some variability in the overall wind situation. So if I show you the wind map associated to this, you can see that you have some large variability between the green and the red on top of this overall, let's say, orange wind situation. So these are creating many different variability that can hinder our capability to reproduce a repeatable wind situation between the model and the SAR. So to try to answer to this question, we have tried to use an analogous methodology, and this is, let's say, the theory that is behind. We start from the assumption that we have enough representative situations that are reproducible from the SAR dataset. And for each ECMWF situation, we are going to go and find the k closest situation in the dataset, we call y, and we are going to estimate the distance between that situation and the other situations. And then we are going to look for the collocated SAR situations, and the way we reconstruct the, let's say, high resolution wind is by estimating a mean, average mean with different weights depending on the distance to the situation we try to emulate of the associated SAR situations. There are many different ways to do it, and we started with a rather simple, I would say, methodology. So here we are just showing a way to estimate differences between the SAR and the model collocated winds, but also between analogous SAR situations. So we are showing a metric that we show here, and so this is a case typically of the region of Girona, where we have two different ECMWF situations, and the way we estimate the distance is a quadratic mean of the U and V wind parameters of all the pixels within the area. And whenever we try to do a difference between the SAR and the model, we first degrade the SAR resolution to a resolution that is closer to the ECMWF model, and then we can compare the two situations. So first of all, we have removed the low wind situations that are not very favorable to SAR observations, because below 2 or 3 meters per second we are within the noise. So we have started at 5 meters per second, and we have split our data set in different parts. So on the x-axis you have the mean distance between the 10 closest situations for a given ECMWF situation. So that gives you an idea of, if you are very far, all your situations, all your closest situations are very far, and you are very close to 0. It means that you have very reproducible ECMWF distance situation. On the y-axis, you have the distance to the collocated SAR. So this means that if you are very far on the top, it means you have very large systematic differences between the SAR and the ECMWF. While if you have less distance, it means that the SAR is closer to your ECMWF distribution. So we expect that on the top we're going to have systematic differences, or not necessarily errors, but differences between the SAR and the model. In green, we're going to have close situations between the SAR and the model, and in red, we're going to have very non-repeatable situations. And this is showing what we are illustrating here. So we have 3 different situations on each row, and what we are showing on this first row, column, sorry, is the ECMWF situation. On the far right, what we are seeing is the situation that is measured by the sound that we are trying to reproduce. And in the middle, this is the one that is estimated by our methodology. So typically we have some north and south situation that are corresponding to what you can see on the top are the wind roses over this area. So these are corresponding to the 2 main wind regimes, because we are mostly very strong north winds and less strong southwest regime. And we can see what we are showing here in green is the root mean square improvement between the reconstruction and the ECMWF initial guess. And what we are seeing is that in these cases of very often met situation, we have a very strong improvement of this estimation. Another case where we have, let's say, stronger differences. Typically, what we can see for this 3 situation is that the SAR data is having, let's say, a stronger gradient to the coast that the ECMWF situation is not necessarily managing to forecast. And again, for this situation, we have, again, a strong improvement of the root mean square error, showing the usefulness of this method. For other situation where we have non-repeatable situation between the models, we can see that here 2 examples where it totally fails because the reconstruction is totally different from what we should have had on the right. The bottom example is, let's say, a chance results where we have an improvement, but it's just let's say a bad chance. I still have 3 more slides and with the conclusion. So overall, we have let's say a median root mean square error for the average performances of 12.5%. And if we are also using some KD3 methodology algorithms, we managed to speed up the process and optimize some parameters that give us the ability to find some optimized also results with a better improvement of the median root mean square error of 14%. And we can see also the evolution of this parameter, the root mean square error evolution, with the distance to the collocated SAR. We can see the color is just the y-axis. But as the distance increases between the SAR and the ECMWF situation, we can see that the reconstruction is really bringing some additional information, up to 70% in some cases. There are some limitations, of course. There is one case for which we have, let's say, very similar SAR situations on the right, but the situation that we're trying to reconstruct is actually very different, even though all the ECMWF situations are very close to one another. In this case, typically, we totally fail to reproduce what we should have had. And in this case, we have been trying to look at the different additional parameters that were available, and we see that the pressure typically is very different. We have a very low pressure situation, which might indicate a strong changing wind regime. So this is what we are illustrating here. We have the SAR reference image, and when we are looking at the time evolution of wind situation, we see that the wind is changing radically from orange with almost 15 meters per second up to a green, which is let's say a gradient of more than 5 meters per second in 2 hours. So we have very likely a very very quick wind transition for which the SAR and the model are not well phased. And I will finish with my last slide. So overall, the investigation of the ECMWF and the SAR-located wind situations have looked at the reproducibility and the usefulness of this data set. It shows that some phenomena lead to additional wind field variability, like rain. Some cases that I just showed are also showing some strong time phasing issue, especially for transient wind situation. But we still manage for other cases that are oftenly image corresponding to a very often met wind situation, some additional useful information in the SAR data. Also, the more the ECMWF differs from the SAR, the better the reconstruction works. There is, however, an issue in this is that we have no inference relation found. Because to be able to do this, we need to know what the SAR measurement is. And one idea of this methodology is to be able to apply it even if we do not have SAR measurements for the specific situation we're trying to forecast. So I've been showing already the improvements of the method overall that are made available within a few seconds only thanks to KD3. And there are several improvements that are identified using, for instance, analog forecasting, but also maybe some more deep learning methodologies if we manage to have a much bigger data set. So far, we have only been using 3 years, but we could put it, make it grow to 6 years and maybe even possibly to 15 years with some additional NVSet data. We are also thinking of adding some additional variables, like some additional metocean variables we mentioned that can further explain the differences, and also work on the spatial region that are best characterizing the wind flow. And this is it for my presentation.